so today we're going to talk about polysaccharides. Now, saccharides are sugars, and poly is many. So these are the chains of glucose that we're going to talk about. Now, the ones we're going to talk about amylose and amylopectin, and together they form starch. So starch is actually two different molecules. We've got glycogen and cellulose. Now obviously there are some obvious differences. This one is plant, this one is animal, and then this one is plant. So this one you find in starch grains. This one is in animals, and you find it in muscle and liver cells. And this one is obviously in the plant cell wall. Okay? Now, some other differences. This one is alpha glucose. Both of those are alpha glucose. This one is alpha glucose. This one, however, is beta glucose. So these three are long chains of alpha glucose, and this one is long chains of beta glucose. Now, your amylose is made only of 1,4 glycosidic bonds. Your amylopectin is 1,4, so that's that one, and this one is 1,4 and 1,6. So I'm going to talk a little bit about those. So if you remember your sugars, and then you have your OH group there. You can form your glycosidic bond between these. So if you get rid of your water, then you have formed a glycosidic bond there. And have a look at one of the other videos to have a look at that process. Now, this is carbon 1, 2, 3, 4. 1, 2, 3, 4, 5. You'd have 6 up there somewhere. So that is a 1,4 glycosidic bond. Now, when you form amylose, you only have 1,4 glycosidic bonds. Now, when you put these glucoses together, they can't form a nice straight line. They kind of get knocked out slightly, and then when you add the next one, it gets knocked out slightly, and the next one is knocked out a little bit more. And so you end up forming this helix. So amylose only has 1,4 bonds, and so it forms this helix. It starts to spiral. Okay, it starts to go around like that. Now that helix is held in place. You get hydrogen bonding. So the turns of this helix, you get hydrogen bonding between them, and that helps to hold that shape. Now, in amylopectin, you also get 1,6 bonds. So there's the first carbon, there's the 6th carbon, and so you get a bond, a glycosidic bond forming there. Now what that does is it gives you branches. So in amylopectin, you get 1,4 and 1,6. And so what you get are branches. Okay? So this one has no branches, and this one has branches. Now, glycogen is similar to amylopectin. It's alpha glucose. You have 1,4 and 1,6, but you have many more 1,6 bonds than you have there. So you get branches. This has many branches. Okay? So these are all compact. They're all nice, good storage molecules. They take up less space. Now, them taking up less space isn't the advantage. Them taking up less space means you can put more in a cell. So the cell has access, or the organism has access to more stored energy. Okay? So they are all compact. They are all energy stores. They are all easily hydrolyzed, which is good because they are energy stores. You want to be able to break them down. Now, if you think about enzymes and attack points, glycogen has many more attack points for your enzyme. So that's the one that's going to be hydrolyzed most easily. Your amylopectin has some attack points, so it's going to be hydrolyzed relatively easily. Amylose is still hydrolyzed relatively easily, but not as easily as amylopectin and glycogen, just because they've got more branches. The more branches you have, the more kind of attack points that you've got for your enzyme. And that kind of stands to reason. If you think about organisms that have glycogen, you've got more potential energy there. If you think about us versus plants, we're more metabolically active. So we need to be able to access that energy much more readily than, say, a plant needs to be able to. Okay? So the structure very much relates to the function. Now, the other thing is they are all insoluble. Those things that would form hydrogen bonds with the water in order to dissolve are kind of tucked on the inside, or they're used up in your hydrogen bonding between the kind of the turns of the helix. So it doesn't readily interact with water, and that's what makes it insoluble. Okay? Now, the last one is cellulose. Now, cellulose is different. It is made of beta-glucose. So these are also all alpha glucose. Okay? Now, I talked about the alpha glucose forming this amylose, not being able to line up in a nice straight line and forming that helix. With beta glucose, every second glucose is upside down. So then you get the next one, and then the next one, and then the next one. So it can form nice straight lines. So it is still all 1,4 only, no 1,6, straight, no branches, but it's not a helix either, it is straight. You get these nice straight lines of cellulose, and you get hydrogen bonding between them. So it forms fibres. And then once you get those microfibrils and macrofibrils all lining up next to each other, on top of each other, hydrogen bonded to each other, you get these cellulose fibres. And then those cellulose fibres are laid down, crisscrossed over each other in the cell wall. So what you get is high tensile strength. And that's what you want in your cell wall. You want your cell wall to be able to resist that turgor pressure from that cell membrane, that full cell pushing out against the cell wall. So each of these polysaccharides has slight differences in their structure, but that very much relates to its function. So these are all storage, energy storage molecules. This one is structural. So these ones are kind of storage. And this one is structural. Okay? So they are all alpha. This is beta. That one and the end one are 1,4 bonds only. The two in the middle are 1,4 and 1,6. That one is a helix. That one has some branches. This one has many branches. This one has no branches. That one has a helix. This one will form a bit of a helix. These ones, the branches are probably too short to start as a helix, and this one is straight. straight. Okay, and this one forms these fibres.